Welcome to the recording of the ELEC1601 crash course. We are SparkSoc, the Electrical Engineering Society. Some upcoming online events include the Element 14 meme competition, so generate your best engineering meme for a chance to win a cool prize. We have a resume workshop with Orcon, or the assembly workshop, which also relates to ELEC1601, like what you guys do in Shoots. And Altium circuit board designing. Altium is used in many industries in the electronics sector, so it's also quite cool to learn. Sign up to our mailing list, which link in the description to a form you can sign up to our mailing list, and also like our Facebook page for updates on this event. Anyway, now I will pass you on to the recording of the event.
Okay, if everyone can see that. So we've got all of our sections set up. So we're going to start off with week one, which is computer system. Then we've got a bunch of encoding stuff, memory, combinational circuits, and then sequential circuits. So after the clock. So there's 5 weeks worth of content that we're going to go through in pretty much as fast as possible. All right. And you'll notice here, it's an any percent speed run. So if I miss stuff, I apologize. But I'm just hoping to give you guys just like an overview before the mid-semester. Just a heads up, pretty much all the notes I have for this are on this speed run. So I'm just going to be using this. If there's things that you want explained a bit further, throw them in the chat. Yeah, that's really all I can say. And then at the end, we'll have a, recording. Do we want to start that?
Started it.
Okay. So that's going now? Yep. All right. Okay, so Lewis is recording, and I assume the recording will be made available.
Just posted to the Facebook page.
To the SparkSoc page, probably under the event.
Yeah.
Okay. So I might leave chat monitoring to Lewis. I'm going to minimize this so I can get the most whiteboard space, so I can just scratch out whatever I've got. And all right, let's get going. Let's start the timer. I'm a little bit nervous. Never done a speed run before in any capacity. So let's go. Oh. Okay, what is a computer system? Now, I'll be honest, first week of content is probably not going to be like so important, not going to be assessed that much, I would guess. All I would say is that when we're talking about computer systems, we've got abstraction. So we've got these levels of abstraction at which we sort of conceptualize our building blocks. So we would be able to talk about, say, writing a program, and then it's based on all of these other abstraction levels. Say it's based on having the physical hardware to implement it, the logic, the instruction code, combining with the system, inputs and outputs. So you've just got all these levels, and at each level of abstraction, you kind of just stop thinking about the things that come before it. You know, like that's the easiest way to do it. For instance, we use levels of abstraction all the time. Say if you're driving a car, you don't really need to know how an engine works. It's like the level of abstraction that you operate the car with is being able to turn the steering wheel and use the pedals, okay? And then there'd be a level of abstraction above that, which is engaging with the traffic, okay? Otherwise, with computer systems, I think an important thing to remember is that there's a lot of arbitrary decisions. Because we're representing things just with electricity, we don't really, there's a lot of ways that you can do things. And it's something I say in my shoots all the time. There's a lot of ways of implementing things. And so if it works, then it works, you know, like it's very pragmatic. There are definitely sort of set standards by IEEE and what we're teaching in the course. But a lot of the time, like if it works, it works. If you've got your architecture that you want to use, then that's what you do. So I think any comments, concerns before we move on from what is a computer system? One thing I will add is with the arbitrary choices, it's important that if you are making these arbitrary decisions, then you've got to stick with it, because computers are not smart. They just take everything deterministically, exactly as it's represented. So that's why it's so important to make sure that you're doing things properly, and just sticking with sort of how you tell it to interpret things, okay? And that sort of leads into encoding. All right, I reckon first section done. Binary encoding. So we know that in computers, we're using ones and zeros, highs, lows, on, off, two states. Now, if we've only got two states to represent things, we want to be able to represent all these numbers and whatever into this binary encoding, okay? So binary only has two states. We can only encode 2 bits, or sorry, 2 information parts. I can't say bit because we refer to a bit as being one binary digit, okay? So for instance, say we have 100 numbers, or say we have 100 symbols or something that we want to encode, and we want a different binary encoding for each of those 100 numbers. Well, how many bits do we need to use? How many binary decimals? Now, this is given by, well, the opposite way is given if we know how many bits we have, which is n, is equal to number of encodable elements. Encodable elements. Okay? So if we had 8 bits for say, it means that we're going to be able to have 2 to the 8 unique combinations, which is 256. Okay? Now going the other way around, if we know the number of encodable elements, but we don't know how many bits, well, we just use log of base 2 of our num of elements. Okay? So in the case of 100, it's going to be something like 6 point, so say our number of elements is 100, we're going to be equal to 6 point something. Now we can't have 6 point whatever bits. We need to have an integer number, or sorry, a natural number, a positive integer. So we need to round up. So we know that we need at least this many. So we round up to the next whole number. So we need 7 bits, okay? If we put 2 to the 7 here, we have 128 encodable elements. If we put 6 in, we'd get 64, and that's not enough. Okay, here, clear canvas. Okay, so now that we've got our binary encoding down packed in 3 minutes, we can start to look at some other number systems or number bases that are useful for us. And they're useful because they're kind of like related to base 2. So if we have a binary number, which is base 2, say, let's go 1, 1, 0, 1, 0, 0, 1, 1. We'll go 12 digits, 0, 1. All right, sorry. Okay, so we've got 12 digits. Well, it's actually quite easy to go into base 8 because you'll notice that 2 to the power of 3 is equal to 8. So if we take up groups of 8 bits, groups of 3 bits, it's like sort of having our base 8, okay? Got something in the chat. That's 10 digits. Okay, I can't count. Okay, we'll go 12. I'm sorry. All right, there we go. Now we've got 12. We're happy. So I've got a group of 3 here, and then we'll have another group of 3 here, another group of 3, and another group of 3, okay? So as I said, we're looking to group it up in 3s if we're going to a base of 8, and then we just look at what the binary combination is. So in this case, say this is our binary combination. We know this first number represents 2 to the 0. This represents 2 to the 1. This represents 2 squared, all right? So we're going to get a number between 0 and 7. So because we're base 8, we only get up to 7. So this one here is 3. 0, 1, 0 is going to be 2. 1, 1, 1 is going to be 7. And 1, 1, 0 is going to be 6. Okay? So we've got our binary number, and this encodes to 6723 in octal. All right? So hex. Well, hex is just grouping it in 4s because 16 is 2 to the power of 4. So if we do these decimal digits in groups of 4, like so, we can find out our hex encoding. So in this case, we're going between 0 and 15. So we'll have 3 again. We're going to have, that's D, pretty sure. And then we're going to have D again. So our hex encoding is OXDD3. All right. Why is it in decimal? The octal number we just got. So that's not, this isn't a decimal number. You can tell because we've got this prefix, this O00. And it's just that when we represent these numbers, we sort of use like our normal digits. You can see in hex, we use letters as well to get those extra 6 digits that we need. All right. So what if we wanted to go from a number? Why do the encoding names have zeros at the start? It's just to show that they're a different base, okay? So we can say OB01, and it just indicates that we're in binary. If we have OO, indicates we're in hex, in octal, and OX just tells us that we're in hex. Because you could have a hex number that looks exactly like a decimal number, right? So you need to specify there. So what about the case when we want to go from like a normal number, say 50, into binary? Well, what we want to do is continually divide by 2 here, okay? So I'll start dividing by 2. I'll put the result on this side and the remainder, or like the result here. So we'll get 25, and that gave us a remainder of 0. We have 12 with a remainder 1, 6, remainder 0, 3, remainder 0, running out of room. Then we have 1, remainder 1, and then our last result is 0 and 1. Okay, so going from least to most significant. So we read it bottom to top. We've got 1, 1, 0, 0, 1, 0, and that should encode 50. Okay, is there anything else in the chat just yet? No, we're all good. Okay, so you can see that if you have this number here, you can go to binary and then just go to base 8 and base 6. Okay, I feel like I'm going to have to speed up. This is challenging. Question. Does this division by 2 work for any base or only base 10? We divide by 2 because we're going into binary, right? So think about it. This is our least significant bit. Oh, sorry. This first division by 2 was our least significant bit. And guess what? This was an even number. So when we divide by 2, it's a 0. When it's an odd number, we divide by 2, we get 1. So that's why we know it's the least significant. And so each successive division is going to bring these, you just take a digit and turn it into binary. Okay, yes, yep. So again, another comment, if we have hex, you can convert each of those hex values into 4 bits. Yes, so if we had the octal number 007, this goes into binary of, you just take these 3 bits, 1, 2, 3, like that. Okay. Yeah, would work from any base. Yeah, so if you wanted to go from 50 straight into base 8 or octal, you do dividing by 8, and then you keep the remainder and just go down it like that. All right. Yeah. Moving on. I need to move this up here. Okay. Encoding integers. So integers, well, we know now how we can encode natural numbers, which is 0 to something. Well, integers, there's two ways. We've got to encode negatives. So we can do sign and magnitude. So we just say we give 1 bit to the sign, say 1 or 0 for the sign, and then we do our magnitude. All right, magnitude. And then we have some combination here, right? So you're saying this is how big the number is. This is if it's positive or negative, okay? Screen share's down. I think I hit something. Okay. We should be back now. Hide floating meeting controls. All right. So we've got the sign, as I was saying, and the magnitude. A 0 will constitute a positive. 1 will constitute a negative. Okay. Yeah, screen should be okay now. Yeah. Okay. Sign and magnitude. If we have a number line, we encode our magnitude and then we encode the direction with our sign. All right. That's one of our techniques. And so what does that get us? That gets us from minus to the n minus 1 to the n minus 1. Okay. That's our range. Now there's a problem with this. We encode 0 twice. We have a negative 0 and a positive 0. So to get around that, we have this ingenious conception of 2's complement. So 2's complement, the steps to go from a normal number into 2's complement is, say we have negative 42. We put 42, so the absolute value of 42 into binary, which will be, we'll just do this quickly. So we go 21 and 0, 10 and 1, 5 and 0, 2 and 1, 1 and 0, and 0, 1. Okay, so we have 1, 0, 1, 0, 1, 0. Okay, so that's positive 42 that we've encoded there. And then we just add a bit at the start. All right. So that's step 1, encode the positive value. Then step 2 is flip all the bits. So just invert them all. Right. You'll notice now that we have a number 1 at the start, which indicates that it's negative. And then we move on to just adding 1. So we'll add 1 here. So we get 0, 1, 1, 0, 1, 0, 1. Okay. That's how we go to our 2's complement number. All right. If you want to extract this value again, if you want to find out what that is in 2's complement, you can do the same step. You can plus 1 and then flip the bits, and you'll get your positive number for it. Okay. And when we do that, we no longer have 2. We get n minus 1. Oh, sorry, my bad. This is our range for sign and magnitude. I missed the minus 1. But in 2's complement, we get 2 to the n minus 1 minus 1. So you can see we get 1 further when we use 2's complement on the negative end. All right. Now, what if we have decimal numbers? Well, again, there's 2 ways we can do this. So we can have a fixed point number where we say, all right, we'll assign 4 bits, 1, 2, 3, 4, ahead of the decimal place, and 4 bits after the decimal place. And then we just know that we'll get an 8-bit number in, and we interpret the first 4 as our binary, positive, sort of like integer part, and then the last 4 will be the fraction. All right. So it's pretty straightforward. It means fixed point, it's always in the same spot within the string. Do we always add a 0 at the front? Okay, this is referring to the 2's complement. Yes, because in 2's complement, you need the sign bit at the start. All right. So you need as many bits as it takes to encode your number, plus an extra bit at the start for the sign. Okay. So you notice when we wrote the 42, it was like 1, 0, 1, 0, 1, 0. That's 42 normally. Then we add the positive sign bit. So we're encoding positive 42. All right. So we've got this fixed point here. Now we might be wondering what our error might be, because obviously we would need an infinite amount of decimal points in binary to encode every single number perfectly, okay? Just like we need an infinite number of digits if we're trying to encode 1/3 perfectly in base 10. So there's always going to be some error. Now, error is a case-by-case thing. So you have like a number that you want to represent, say 2.953. You see what you can represent and you find the difference, all right? But you might see in this case, the maximum error that we're going to get is going to be half of this value here. So this is 0.5, 0.25, 0.125, 0.0625, okay? So half of this divided by 2 is going to be our maximum error. Because if we look at our number line, we're able to perfectly represent all these points going up in terms of 0.625, so 0.125, and so on. So if we had a number that we want to represent here, then this is going to be our maximum error, okay? Now, floating point numbers. We have a specific representation. We have sine, a mantissa, and an exponent, right? And this goes into this form. So we'll have plus minus, we'll have 0 point something, and then we'll have 2 to the power of exp, okay? So the definition of the mantissa is your leftmost one is directly to the right of the decimal point. So if we had 0.001, our mantissa will be 0.100 times, or we can represent it with a mantissa and an exponent times 2 to the 3. 1, 2, 3. Sorry. 1, 2, 1, 2. Sorry. 2 to the 2. And going the other way, say we had, sorry, minus 2. Going the other way, say we had 100.00. This representation goes to 0.100 times 2 to the power of 1, 2, 3. Okay? So exponent is usually encoded in 2's complement. Mantissa, just remember, number 1 always has to be exactly to the right of the decimal point, all right? That's the main takeaway. And then sine, again, is just 0 or 1, all right? So apologies if I'm skipping through stuff. I know that I am, but yeah, this is a speed run, or it's a very crash course. We're going through what, 5,000 signs differing. Okay, we'll go to this example, just something in the chat. Why are the powers and signs differing? Not exactly sure what that question is. So with the example of one, okay, in mantissa. Mantissa is just like mantissa is always going to be positive because we encode our sign in the first bit. So with the example of, let's say 0.1, I'll just do it like this, times 2 to the power of 3. So that's a positive. Okay, it depends on how many bits we assign to our mantissa and exponent. Let's just say we have 3 bits for the mantissa and 4 bits for the sign, for the exponent. So if we wanted this in binary, we'd have 0 for the sign, put our mantissa in, 1, 0, 0, and then our exponent in 4 bits, which will be in 2's complement 0, 0, 1, 1. So we have 0, 0, 1, 1. So that's this representation in sign, mantissa, exponent. Exponent always in 2's complement. No, there's never always, always is a very powerful term when it comes to making these arbitrary decisions. We can do things like bias our exponent. If you know that you never have decimal numbers, you just have massive numbers, you can have a purely positive exponent. But generally, if it's not said in the question, I would assume two's complement. How do we assign the bits for mantissa and exponent? Oh, okay. And this is, usually it's going to be based, usually you'll be told how many bits you have in total. You know that one always has to go to the sign. And so you have to make the decision based on mantissa and exponent. In general, you want to make sure that you get the entire range. So you look at the highest number that you need to come up with. Say 300 is the highest number in your range that you need to encode. You'll make sure that you're, so you know that 300 requires, well, it'll be 9 bits. 300 require 9 bits to be perfectly represented. So you know that your exponent has to at least be able to shift 9 places, all right? So if you're in 2's complement, you know that that's 4 bits. So now you've made that decision, you check with the number you have left over. So if we had 8 bits all up, 1 for the sign, 4 that we're using for the exponent, 3 for the mantissa, you try out with your mantissa and do it with your exponent. If you can get over 300, then you're sweet, you've made your decision. If you can't get over 300, if you can't get your whole range in, then you may need to vary the bits in your exponent. So you choose the exponent first to cover the range. All right. So that's it with encoding. 24 minutes in. It's not too bad. We'll see. So next thing, memory operations. Luckily, there's only 2 of them. We have read and we have write. All right. When we consider memory, I want you to think of it as a big table. We've got memory addresses down the side, and then we've got data in each of these. Okay. This is increasing address going down. So we've got these 2 instructions to deal with memory. We can say read at an address. And what does that give us? It just gives us the data at that address. Okay. So say this address here is OX100, and we've got the binary number 10110111. So this is 1 byte memory. Well, if we read at OX100, that equals 10110111. Okay. What about write? Write takes in an address and a value. So we could say write this same value somewhere else. So we could say write at OX101, that value, and boom, goes in there. All right. So these are our 2 operations. Something to note that's going to be important, unless we have assigned this data, unless we've written in the data, after you turn on a memory chip, you don't know the values of what you have. All right. So if we said, all right, this chip has just been turned on, this memory's just been turned on, want you to read at this address, what's the value? It's not 0, it's not something we know, it's just unknown. All right. It's undefined. Fresh memory, undefined. Remember that. I'll be disappointed if people get that wrong. I don't see results, but I'll be disappointed. All right. So another question I see a bit is reading in terms of 4 bytes. All right. 4 bytes, read and write. R/W. That's awful. 4 bytes, read, write. Well, a lot of people seem to get confused by this, as indicated by Ed questions. All it's saying is that when you say read at an address, it goes to that address, or it goes to, I see why there is confusion. So when it says that your memory can be operated in 4 bytes, it means that it probably will be operated in 4 bytes. So you assume that it's going to read and write in 4 byte chunks, okay? So it's going to operate in these chunks, but say we started at 0, say this is our 0 point, it's already kind of going to have these chunks defined. 1, 2, 3, 4, all right? So it's already gonna have these so we've got 4 bytes of memory, byte in each cell, it's already going to have like these blocks sort of like understood and like known, so that it can only access like these 4 bytes at a time. So if you said read OX001, well, 001 exists within this predefined kind of byte. So it's going to read this 4 byte block. All right. Now, it can be a little bit confusing. I'll be honest, that's pretty sure that's how it works. But if you get a question and it doesn't say something like, oh, which 4 byte block is this going to be part of? Which sort of thing is this going to be part of? Then it could be interpreted that you just take the address as is, don't worry about the blocks, and just go for after it. Okay. I'll be honest, I'm not sure. We need to look at the questions and just sort of keep that in the back of your mind. If it always works out, then sweet. Otherwise, yeah, because all these things are kind of arbitrary, it's kind of hard to say a definite answer. All right. So say we read in 4, we write in 4. So if we write at OX000, our address, we write this byte. Well, what's going to happen? Starting at OX000, we're going to get 1, 1, 1, 1. It gets written 4 times, 4 bytes. Okay. Memory size, half an hour mark. So memory size is basically just looking at how many cells you have, how many addresses you have, and how big each of those cells is, and multiplying them together. All right. So if you've got something that has 1,000, oh, it's not going to be 1,000. It's going to be like 2 to the 8 addressable memory. Addressable. So you got 2 to the 8 addressable or 8-bit addressable memory. Means that you're going to have 2 to the 8, so 256 memory locations. And if it says 1 byte cells, then you know you've got 256 addresses and they're each 1 byte. So you've got 256 bytes. All right. Again, if you've got 2 to the 16, say, addressable, and then it says you've got 2 byte cells, well, you know you've got 2 to the power of 16, which is 63, I think it's 63,000 something. Well, you times that by your 2 byte cells, that's how many bytes you have of your memory, okay? It seems to make sense to me. I hope it makes sense to everyone else. How do you find out the size of the address bits? It'll tell you. It'll say, okay, all right. So if you get told, say you've got like a 1 kilobyte memory, okay? So you get told that you've got a 1 kilobyte memory size. And you also get told that it has 1 byte cells. You could be asked, oh, how many bits are used to encode the addresses in this memory? Well, you've just got to encode this or decode what this KB means. So kilobytes means 2 to the power of 10. All right. Megabytes, 2 to the power of 20. Gigabytes, 2 to the power of 30. All right. So if you have that, well, you know that you've got 2 to the 10. Well, that's your total size. Divide that by your 1 bytes and you get 2 to the 10. Well, you'd look at this number here. And so you're going to have 2 to the 10 bits for your memory. If you get something like, could get something like 32 megabytes, Well, that's 32 times 2 to the power of 20. And what's 32? That's 2 to the power of 6. No, it's not. 2 to the power of 5 times 2 to the 20 is equal to 2 to the 25. All right, so that's how you can do these operations. All right, data storage. Now we've got our, we've got a whole bunch of primitive types. Like say a lot of the time you're going to have characters, 1 byte. Integers, they take up 4 bytes. You could have a double, takes up 8 bytes, right? Like these are all just defined things. There's a table on Canvas somewhere that's got all the Java types for these sizes. And then, yeah, in your question, you could get told, or you'll probably get told how big each of these things are. So like it could say, oh, you've got 2 bytes for your character or whatever. All right, so that should be told. Just, I think something to talk about is little endian and big endian. So little endian, big endian. What do these mean? Well, you see how you got this int and it's 4 bytes. Well, that means that you're going to have to, when you say 2 bytes, does that mean 2 characters? Oh, I'm just saying that you could get an encoding where each character is 2 bytes or something. So you could get that. It'll probably be defined in the question. Now we've got little endian, big endian. You notice that we got these integers that are 4 bytes, which means that we need to split up our number into 4 cells, right? Well, where do you start? Do you put your, all right, so let's say we've got this integer OX 1, 2, 3, 4, 5, 6, 7, 8. So do you put your most significant bytes first or your least significant bytes first? Answer is it doesn't really matter, or well, for anything that we're doing, but you just need to know that that's what you're doing, okay? It's an arbitrary decision, stick to it and it'll work. So little endian means that you store your least significant first. So this is addresses increasing. This is your lower address. And then big endian means that you put your most significant bits first, okay? Data storage, I think, yeah, array is a different section. So storing an array. Well, if we've got a whole bunch of stuff, so we've got 10 characters, and they're each 1 byte, well, then we just have this memory and we store times 10, we'll have a whole bunch of bytes, okay? So we'll have 10 bytes and we store this array in here. How do we know how many bytes we have in there? How do we know that it's an array of 10 characters? Well, that needs to be defined somewhere else. That can be a number like stored somewhere else in binary, at some other memory address or whatever. Or we could do the Java way of doing things. And at the start of this 10 characters, we have, oh, this should be, we've got 4 bytes here, which is an integer that tells us how long the rest of this is, all right? So if you've got an integer array, if you've got a Java array, remember that there are 4 bytes at the start that tells you how long that array is, okay? And that's going to be specified in the question, whether it's Java or whether it's normal, okay? Or just another computer system, okay? Right, so that's storing away. It's just a bunch of things sort of lined up together. Now, what you're probably going to be asked about is if you've got like structs or something, you could have a array of, let's say you've got a struct and it's made up of 10 characters in an array, and then you've got 2 integers not in an array, and then 1 float. And it asks how much space this is going to take up. Well, you know that you have, and assuming, let's just say this is in Java, say these are 1 byte each, you'll have 10 bytes plus 4 for for the total array. This will be 2 times 4 bytes, let's say. This will be 1 times 4 bytes. So your total struct is just the addition of all these. So 12, 28, 26. Okay, sorry, I know, I'm just blasting through this stuff. So again, if you see something that has like array, say we're talking about this character array and it wants the position 5, well, in Java, that just means that we start at this address here. So this is 0x00. We'll get 00 plus the size of our characters, which is 1 byte times our index, okay? And that's why our indexing starts at 0. Because if our index is 0, we would start exactly at the address when the array starts, okay? So in this case, we want the 5th element. It's going to be at position 0x05, all right? So here somewhere. Now, what if we had a Java array? Exactly the same thing, but you've got to add 4 bytes to skip, all right? So you know the first element will start 4 bytes after the position where your array is defined, all right? So you've got to add that +4. So, you know, when we've been doing this, we've got our memory, and you know, this is just another number, all right? Which means that we can store it within our data, okay? So we could specify that, all right, we'll store this address here, and say that's our address, and we've got all these other memory spots. And this is called indirection. When we store a memory address, which says that we want to point to somewhere else or indirectly access it. So you might get an operation in your code that says, oh, I've put an address to something I want in this spot. So what happens? You're going to go to this spot, read the address, jump to where it says, and then return the data that's in there. All right. Now, you can do that as many times as you want. You could go from this spot and say, oh, there's a memory address here, go to another one, and then return that value. You can indirect as many times as you want. Now, in this case, where it's just this simple indirection, it doesn't see much point because you could just store the initial number here. But in cases where we have references to objects, such as in Java, we sometimes don't store like the object in a position. We'll store the address of that object somewhere else, okay? And say for strings, which is just a bunch of characters, it can be much more useful to store a bunch of like string addresses. So like address 1, address 2, address 3, for all these sort of like, for all these strings, string, and these could be stored wherever you want, all right? But you know that if you wanted to access all these strings one after another, you can just iterate through these indirections, okay? So that's one example where they're pretty useful. All right, memory segment done. Any questions in the chat? I'm gonna take 10 seconds to take a drink. No, we're not going to need to know. You're not going to need to know how it knows an address, because it's kind of defined when you do the programming. Okay, we might see that when we do AVR, but I don't think we need to know that. If we do, yeah, well, I owe you a mark. But like, I honestly don't think you need to know that. I don't think I've seen it anyway. Okay. Boolean expressions. Now we're getting into combinational circuits. Second last module. Now, Boolean expressions. We have we know that we can represent data with bits, so 1 or 0. Well, what if we had a variable that was x, and we knew it could have the value 1 or 0 or 1, okay? What if we had a bunch of variables that could all have these values, all right? Well, we can start to do some operations with these so that we have a combination, and we start to find out like truth table things. So it's like if x is 1 or true, and it's combined with x and z in a certain number of ways, and y is true when z is false, then what's our output going to be? All right. So there's a number of ways that we can combine these variables. So the first we'll talk about being and that's basically the same as timesing these two together. We'll just x, y. And it's just saying x and y both need to be true for the output to be true. Okay. So if we represent these with zeros, 1 and 0, well, if we had 0 times 0, we expect it's going to be 0. Well, 0 times anything is equal to 0. But when they're both 1, we get a 1. All right. So this is a bit of Boolean algebra. Now we'll look at OR. So with OR, we represented x plus y. So we can say x or y has to be a 1 to be a 1. So say 0 plus 0, we know that equals 0. 0 plus 1, 1 plus 0, that's going to equal 1. 0 plus 1 is equal to 1. About 1 plus 1, we think it equals 2, but it sort of just caps out at 1. It can't go any higher than 1. All right, so it's 1. Then our last thing is a lot more simple. Getting a phone call, ignore it. We've got not. All right. So we know that we just have x and it's an inversion. So it's when x is equal to 0, the output is equal to 1. When x is equal to 1, output is equal to 0. Very straightforward. Now we can start to build up these combinations of circuits and then like invert that, whatever. All right. So you can generate these combinations and all go down to one value if you were to sub things in here. Let's actually do this example. Let's find it when x is equal to 1 and y is equal to 0. Let's see what the output is. We'll just sub it in. So you get 1 times 0, 2 brackets first, then we'll do inversions, then we do multiplication, then we do addition. So it's sort of like normal algebra. So we do brackets, 1 plus 0, inverted equals, well, this goes to a 0. 0 plus, we have 1 plus 0 is 1, inverted is equal to 0 plus 0. All right, so that's how we found it if x and y were both equal to 1, were 1 and 0. All right. Boolean expressions, anything else that needs to be mentioned? Probably, but I'm not going to do it. All right, so now that we've got this algebra, how can we represent that physically? Well, if we say that our AND operation is represented by this, oh, that's awful. I'm not letting that stand. This gate here looks like a D. Well, I've drawn it to look like a D. Well, if we have these inputs, we can say, all right, well, our output is just x times y. So we're just mapping from our expressions into like a physical gate. Yeah, and I will get to product of sums. I've got canonical forms. It's our next thing. Yeah, yeah. POS could mean something else, couldn't it? Okay. So in this instance, we've got and like this. We've got an or. Oh, sorry, 1, 2. Oh, can't draw. It's just like a pointy looking gate. We've got not, which is this triangle thing with a little dot on it. A lot of times you'll see inverters just as like these little circles put on the end of something else. All right, so we know how all these ones work, but what about NAND? What does NAND stand for? Not AND. So you just take whatever this is, so you got X, Y, and your output is just X, Y inverted, right? So if we did the truth table, oh, that's bad. You're going to have X and Y, 0, 0, 1, 1, 0, 1, 1. Well, it's the opposite of the AND. So the only case where it's not 1 is when they're both 1. All right. So we've got that one. Then we've got a NOR gate, which is an inverted OR gate. All right. Then we get these sort of fancy ones. We've got an exclusive OR gate, which means if we've got, say, XY, and the definition and XOR means like exclusively OR. But the definition, if we look into like multi-input gates, is that if any of our inputs if we have an odd number of inputs equal to 1, out is equal to 1, right? That's our definition. So if we get an XNOR gate inverted, if we have an even number of inputs equal to 1, output is equal to 1. So that's the general form. And that's probably how you should think about it. Because what if you get like a disgusting looking XOR gate with 4 inputs and you got no idea what's going on? Use this definition. Odd number of inputs equals 1, it's a 1. All right. And all of these can be extended into multi-input versions. So you can have a 3-input and just means that X and Y and Z need to be equal to 1 for it to output 1, because the expression is just X, Y, Z, right? And you can just make these out of like 2-input ands, because you can do this. You could do it more simply, but it's okay. It's a 4-input and. So we got this. Okay, so if we had 3 1s and 1 0 is your input into the XOR, that would be true, correct? Right. I'm just realizing now that I skipped over a bit of simplifying algebraic expressions. I don't think I'm going to go through that, to be honest. That's sort of like it's like a practice thing. It's not super useful to just go through the theory, I reckon. Okay, so now we've got this big set of logic gates that we can use to do stuff. We can tick off that segment. So canonical forms, sum of products, product of sums. Now, why do we want to do this? It's if we have a circuit and we want the algebra. All right. Well, what if we had the algebra? Oh, sorry. Oh, now I'm thinking. Okay. What if we had the algebra and we wanted, okay. I got to take a second. Circuit to algebra, do the truth table, product of sums. Okay. All right. So circuit to algebra, this in-between step is truth table. And the algebra is going to be our product of sums or sum of products. Okay. And then if we've got an algebraic expression and we want to find out what the circuit is, we have to go to algebra, we do our truth table, we get our product of sums, sum of product, and then we build a circuit from there. Okay. 4 1s output 0. Yeah, sounds right. For an XOR. All right. So these are sort of like the steps that you need to take to go from circuit to an algebraic expression. Go circuit, build your truth table. You get an algebraic expression using sum of product of sums. And if you've got an algebraic expression and you want a circuit, you have to find the truth table, generate your product of sum of product, and then go to a circuit from there. All right, so we're going to look at how to do the product of sum of product stuff. All right, so let's say we've got this truth table, x, y. This is going to be real simple. 0, 0, 0, 1, 0, 1, 1, 1. And output, let's just do something weird. 1, 0, 1, 1. Okay? So this is our truth table. Say we've got a circuit. We've put our x in, each of our x and y's in, and we've got our output. We've gone through, we've generated our truth table. Now we want to go to a product of sums or sum of products representation. So we'll start with sum of products, SOP. And just while we're here, I have been putting up like tutorial videos on Canvas. Go check them out if there's things that you want explained in more depth than this super quick thing. That should be pretty helpful. It's all out there. Anyway, so sum of product. First thing we do is look at all the rows where we have the output equal to 1. Okay? Output equal to 1. And then we generate a whole bunch of products. So we had 3 of them here. So we'll generate 3 products of XY. XY product because they're multiplied together. And then you look through and you see this first term is going to correspond to this first row. Second term corresponds to the second row. Third term, third row. If your term is a 0, you invert it. Okay? So we'll invert X and invert Y. In this third one, we only need to invert Y. Last one, no inversions at all. Last step, add them together. Okay? So if you plug in any value, any of these values, combinations, into this expression, you're going to get this same output. Okay? So let's just think about if you put in 0, 1, well, 0 is going to give a 0 for the Y here, so it's 0. X is 0, whole thing is 0. X is 0, whole thing 0. So you get 0 out. All right? But otherwise, if you put in one of these combinations, you're going to get one of those terms that becomes a 1. Okay, so the whole thing goes to 1 because they're all added together. Now we'll look at product of sums. All right, and I'm just going to change this output a little bit. Okay, so this is no longer the sum of products for that. It was for before. So product of sums. Now what we do, we look at these 0 rows. Okay, and then we write out to a sum for each of the terms here, x plus y, x plus y. And then for each of these, if we see that the y is a 1, if each of these terms, if any of these terms is a 1, you invert it. Okay, invert that. Then we've got, well, they're both 1, so we invert both of them. All right, last step, multiply them together. So you can see this is called a product of sums because you've got a bunch of sums all producted together. This is a sum of products because you've got a bunch of products summed together. All right. Now, again, if you input everything into here, input these inputs here, you're going to get, well, the same output. Okay. So that's our sum of products and product of sums. So we can do this one here, but we're only up to this stage here in this process. Algebra, truth table, sum of products, whatever. How do we generate a circuit from here? Well, we know that we have 2 inputs. So we've got X and Y. We have a normal X and an inverted X. So at start, we can just say that we've got one of each. Okay. Now you notice that we have 3 product terms, which means that we need 3 AND gates because that's the gate that does that operation. So we've got 3 AND gates here. And then we have 1 big sum. So they're all going to feed into 1 OR gate. All right. So now we just connect up our first term into this first AND gate, and they're both inverted. So take these in here. Then we've got X, Y inverted, X, Y inverted, and then we've got X, Y. X, Y. These all come into this OR gate, and that's our output. All right, that's our sum of products. Okay, so we've got our inputs here. We've got a AND gate for each of our terms, and then we've got an OR gate to put it all together. All right. So what about our product of sums? Well, again, we're going to have X, Y as, well, Y, I'm just going to leave it there, even though there's no non-inverted Y inputs. And what have we got? We've got a bunch of additions. So we've got OR gates into an AND gate, all right? And then we just match them up. So we got X and Y inverted. Then we got X inverted and Y inverted here. All right. So that's our circuit representation. Okay. Very straightforward, I guess. Okay. That's sequential circuits. Whoops. Sequential circuits done. So sequential circuits are things that you can't really you can't feed them back into itself. So for example, this is not a sequential circuit because we'll never know what that value is, okay? Because your output is dependent on your input, okay? So what if we want to start storing memory, okay? So we can have our sequential stuff, we can do all these processes, whatever we want, but we're not going to be able to do much because we can't store it across time. That's why the clock and our, sorry, I was saying that there before was sequential circuits, they're combinational circuits, my bad. So we're looking at sequential circuits and they're based on the clock, all right? So the clock is this square wave thing here. We've got time going this way. So this point here is earlier in time than this point. The anatomy of the clock signal is, this is called a rising edge because it's going from low to high. This is called a falling edge because it's going from high to low. This point here is high level. This point here is low level. And then we've got a frequency, which is based on our lambda, which is our wavelength. Well, sorry, that's our wavelength. But it's also, if we look at it in time, that's our period. That's how long it takes one cycle. Frequency is equal to 1 on the period, okay? Just in case this comes up, all right? So we've got the clock there. That was a very simple thing. So what do we have now? We've got these flip-flops. So flip-flops are circuits that are going to be based on the clock. So they're called synchronous, and they're going to do stuff as the clock changes, okay? So I'm actually going to start with a D flip-flop because it's the most simple. So D flip-flop looks like this rectangle, D input, Q naught output, okay? You can also see this written with a little thing here, but it'll also say Q naught. That isn't like doubly inverting Q naught, just so don't get confused. So now we have an extra input. So this is our input, and we have clock coming in here, right? And so there's different ways that we can make these sensitive to the clock. So remember we had the clock signal like this. Well, at the moment, this is a rising edge, a high level sensitive circuit, right? For a D flip-flop, in is just equal to out. Well, so what does high level sensitive mean? It just means that any time that our input is changing here, it's copied. During this phase here, when the clock is high, we're evaluating our circuit. So it's like a normal combinational circuit. Then during this time here, when it's low level, we're just saving whatever our last thing was, okay? So a note coming in here, it evaluates, it goes back down, and then just saves it until the next thing, all right? So we can take the inverse of that by inverting our clock signal. So now it becomes low level sensitive, which means that it's saving results during this high level, and then it's acting like a combinational circuit during this low level period. So if we had an input here, I'll get there. What's our time? 1/4 past. That's okay. So say we've got an input here, then our output's just going to copy it at that phase. But say it changes in the high level, does nothing, because it's just storing our value. Okay, so those are level sensitive circuits. Now we've got edge sensitive circuits. And what happens with the edge sensitive circuits is that they only evaluate the input. They only act as a sequential circuit, a combinational circuit, sorry, at the edges. So this triangle here means that it's a rising edge, all right? So every time we're at this rising edge, so these times here, then based on our input, we generate our output only at that point in time, okay? And then if we invert that, that means falling edge. So now we're looking at these falling edges as a time when we execute. So it's only at that point in time we evaluate our input and output, okay? Or our output from our input, right? Okay. So what's the truth table of this D flip-flop? So we've got our input D, and we've got an output here. Now, our output is called Q, but our output is going to be after the next clock edge, okay? Let's say rising edge. After our next rising edge, there's going to be some input. And we denote that it's after the next clock update by saying time +1. So saying it's in the future, this value will update, okay? So QT, sorry. All right. So if at some time our input is 0, well, when the next clock edge comes in, our output is going to be 0. If our input's 1, next clock edge comes, input's 1. Okay, pretty straightforward. So we've got that one. The next one that we're going to look at is an SR. I'm going to make them all rising edge. SR, Q, looks like a K. Q naught. All right. So we've got SR and QT plus 1. Well, so if they're both 0, we just hold what our initial value was. And we denote that by saying QT. We output what our current value, or like what our value was before the clock edge, okay? If S is 0, R is 1, we output a 0. And it's like saying reset. So it's like if it's a reset signal, give a 1 in the, we get a 0. If we have 1, 0, it's like set, so it goes to 1. They're both 1, big question mark, undefined, don't do that, okay? It's not robust enough to deal with 2 1s as an input. All right, that's a big flaw. So we have something else called the JK flip-flop, all right? Another box, rising edge, J, K, Q, Q bar. Does the diagram show which edge it's sensitive to? Yes. So you can see that this is sensitive to the rising edge. And if it was sensitive to the falling edge, it would be like an inverted clock input. It'd have like a little bubble there, okay? Yeah. But say this was like a high level sensitive SR, it would just mean that, say, when it's in the high level phase, when you have SY equals 0, say this combination here, it's just going to output that straight away. All right. So we'll just build this truth table here, J, K, Q, T plus 1. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so JK operates the same way as the SR for the first 3 columns, okay? And instead of being reset here, it's like a kick, so you're kicking out the value, so it's down to 0. J is like jump for 1. To be honest, I don't know what the J and K actually stand for. I don't know why it's called that. But the 1, 1 now has a defined value of Q bar, okay? So if J and K are both 1, then this value just inverts at the next edge, okay? Flip-flops. All right, so let's do a quick example. Let's just say we've got D, Q, Q bar. And I'll take Q bar, actually. And we'll just put that into double input for a JK. So that's JK. And then we'll bring this out and put that into an AND gate. All right. What? Jump, knock. Okay, yeah, jump, knock, whatever you want to use for J and K. Right, so what I'm going to do here is we're going to define this input D, we're going to have an output, and then we're also going to say what these like Q values. So this is QD, and I'll call this QJ, all right? Quick example, we're sort of coming to the end. So this is our clock signal, right? So clock, we've got D, and let's just say, I don't know what the answer is going to be. I'm just going to do it like this, right? That's our D signal. Now we can define what we'll have QD and QJ, all right? So looking at this first one, we've got D. It's rising edge. Sorry, I should have specified that. Both rising edge. So the only point in time that we really care about is at these rising edges here, okay? So we're going to do it in blocks, sort of like looking at these rising edges, okay? Now, at this first one, we've got, we'll just say everything starts at 0, all right? 0 and 0 up until this first edge. Now we evaluate and see if anything changes. Oh, I should probably have one for output here as well. Out, well, we'll say out is 0 as well. Okay, cool. So so D is 0 here, which means that the next Q after the edge is going to be 0 as well. So we can just write that in for the next period until the next edge. Then we can look at our other things. So in QD0, we've got this inverted output coming through here, which is going to be 1, right? So J and K are actually 1 at the moment, all right? So when J and K are equal to 1, it means that you flip your value. So this actually becomes a 1 here, right? So we had output, well, QD is a 0 and QJ is 1, but it's an AND gate, so it's 0. All right. So we'll look at this next phase here. We've got D equals 1 at the edge. So we now have QD is equal to 1. Well, now QD is equal to 1. Well, we have Q is equal to 0. So we've got a 0 coming in. So we look at this, and if J and K are both 0, we just retain our value, which means that QJ stays high. All right. So this output is meant to be 0 up until here. And look, we've got QD and QJ both equal to 1. So cool. We've got an output of 1 now. We'll just do our last stage here. I'll use this multicolored pen. So D's gone back to 0, which means that QD, when it's evaluated, is 0. So, oh, it's a glitter pen. That's cute. So now we've got a 0 here again, which means that this is going to be a 1. It's a 1, which means that this JK is going to flip, puts us back down to 0, which means that our output is going to be 0 as well. So that's just a quick example to show the combination of two circuits together working across time. All right. So look at each of your edges, find out what all of your values are just before that edge, evaluate it, move to the next edge. All right. Well, finite state machines, last step. All right, so a finite state machine, well, it's a set of finite states. So you've got, say, state 1, state 2, state 3. This could be any system. And say you want to move between states, right? Well, you could say, all right, well, sometimes I want to stay in state 1 depending on some input. Let's say we've got an input I, which could be 0 or 1. So say our input is 0, stay in state 1, or else you transition. Say this one, you always want to move to state 3. And say this one, 0, 1, okay? So it's just a way of having these particular states and a way of moving between them, okay? So how does this tie in to what we've been doing with all the flip-flops and all that stuff? Well, we can actually represent, why is that on? Oh, that's on annotation. I'm pretty sure down here. So we can actually represent these inputs and states as binary combinations. So say we've got these 3 states, we can say S1 is equal to 0, 0, 0, 1, S3 is equal to 1, 0. Okay, so we've got that. We've got an input, which is just 1 bit. Well, what if we had a truth table? Sorry, 1 second. Sorry, I'm just in the middle of something. Still on speed run. No, I'm not home. Okay, see ya. Okay, very professional. So we've got, well, we can use a truth table to represent based on this current state and an input where we're going to be next. So we could have, like, we'll just call this S1 and S2 and our input, and we'll be able to find our next S1 and S2, okay? So you can see that we're just mapping our like current state with our next state based on an input. So we'll just fill this out real quickly. So you got 0, 1, 0, 1, 0, 1, 0, 1. This is a fast way of filling out truth tables. 0, 0, 0, 0, 1, 1, 1, 1. Okay. So we're in state 1 and our inputs are 0. We stay in state 1. So it's 0, 0. We're in state 0, 0. Inputs 1, go to state 2. State 1, we're in state 2. Well, in state 2, we always go to state 3, regardless of the input. So go 1, 0, and 1, 0, 1, 0. Yep. So now we're in state 3. If it's a 0, we go back to state 2, 0, 1. Otherwise, we go to state 1. And this one is just unused. All right. So you can see that we've got this. I might just delete these 2 rows. So we've got this transition, okay? But we know that, say this transition was based on a clock. Say these transitions were happening every clock edge. Well, we could define these as like S1 plus to say that it's the next state, like at a future point in time. So based on our current state and an input, we can get a next state. And that's sounding kind of similar to what our flip-flops were. We had like an input, and then if we knew the input at the next clock edge, we'd have a specific output, okay? So that's where this all kind of ties in. And we can actually create a circuit that represents this finite state machine, okay? Now, how do we do that? We use sum of products or product of sums. So I'm going to do sum of products here. So I'm looking, we've only got 2 1s in each row. So for S1 plus is equal to, well, you'll just see a real quick sum of products going ahead now. So we've got S1 inverted, S2 off world record pace now. Time lost in. Oh no, no! This is a world first. All right. So whatever I do is a world record. Okay. But I don't know. I should have paused. How long did the phone call go for? 15 seconds. I'm going to pause it for. I'm going to pause for 15 seconds while I explain. All right. We're back on world record pace, everyone. So we got S1, S2, and then we get I inverted. Okay, plus, all right, that's enough time. So we've got, then we've got S1 inverted, S2, and I. All right, so that's our sum of products for S2. Then we've got this one is equal to S1 inverted, S2 inverted, I, and S1, and okay, S2 inverted, I inverted. All right, I hope that's right. I'm running with it. Okay, so now we get this product of sum stuff. Well, I'm going to do 4 AND gates for it. We're going to have S1, S2, and I here. Going to have an inverter for all of them. Okay, and then we just link them up. So these two will correspond to S1 plus. So we've got S1 inverted, we've got S2, now we've got I inverted. All right, this is going to get messy, I apologize. S1 inverted, S2, and I. All right, that's our first one. They'll feed into an OR gate, okay? And then we've got S1 inverted. I'm down at S1 here. Then we've got S2 inverted. And we've got I inverted, and S2 inverted. Okay? And that feeds into here. Okay, what's the missing step? Well, we don't want this value to actually change. We can say that this is sort of like S1 plus and S2 plus, but we only want that to become our next. All right. Yeah, I could never be a speedrunner. I'm too dishonest. Reported. Yeah, well, speedrun.com, I know the mods, so I'll just get it in there anyway. All right, so we know that this is the next state, but we need to bring the next state into the current state. How do we do that? Handy dandy little D flip-flop, okay? So we throw in a D flip-flop for each of these state. Oh, that's awful. Q, right? Oh, sorry. Feeds in here, feeds in here. And guess where these go? These are your current state, okay? Because you have your next state, and when the clock edge goes, it becomes your current state, all right? So this cycles back around to state 1, and this cycles back around to state 2. And the cycle continues. You can see how you change your I every time, but your states just sort of cycle around, okay? All right, we're nearly done. One more thing, outputs. What if we want some kind of output from this circuit? Well, there's two places we can generate them from. We can get an output from our state, or we can get an output from our transition. If we take it from the state, it's only based on our current state, and it's called a Moore machine. If we're taking it from a transition, it's based on a current state and a current input, and that's called a Mealy machine. Write that in there, Moore, Mealy. Oh, they should be capitals because they're names. All right, so what if we wanted to implement that in here? Well, what does this represent? So this here is our next state, and this here is our current, right? So coming out of here is our current, coming into here is our current, and then here is our current input, okay? So if it was a Moore machine, you're just going off your current state, so you could go into some output generator here, some combinational circuit, right? But if it was a Mealy machine, would depend on the input as well, well, you can take it from here again into some output, but you also have to take your input as well, all right, to some output. Now, it's looking pretty messy, but what if you were to take your output from here based on these two things? Say that's your output, an AND gate there. Well, that is actually dependent on your current state and your current input, because you can see that these are all your current things and they're just going through a combinational circuit. So in this case, it would be a Mealy machine, okay? I don't know. I think that's kind of it. I think that's the, can I end the speed run now? Is that it? I'm sort of waiting on some kind of confirmation. If there's anything I've missed. Yeah, time. Okay. Oh, 24:54. Woo! That's the most focus I've been on anything.
Give a huge round of applause to Nick, or virtual round of applause. Yeah.
How many people do we still have?
Oh, we have
43. Wow.
Anyone on the couch want to
Yeah.
come?
So up next we've got ELEC1601 done quick.
Let's see if Johnny can beat Nick.
124:54. 5 weeks of content. Hey, this sounds like when I was studying for this exam.
Yeah, basically.
Maybe would have done
I
it
think
a
that
bit
was
quicker.
the same with me. I probably spent the hour before the exam studying for this.
Yeah.
Yeah.
Yeah. That was all right. Yeah. So if there's questions.
Oh yeah. Any questions?
I've got about 15 minutes before I have to go and teach this subject for an actual tute. But yeah, if you've got questions now, feel free to go ahead. When will I be attempting this record again? No, this is a one and done. This is a once in a lifetime kind of run. You don't just get up every day and decide, yeah, I'm going to do an any percent 1601 speed run. Yeah, so if you've got questions, ask now. Otherwise, I'll try get on ed a bit before the mid-sem, and sort of just get through as many as I can.